Hello and welcome to the third part of Lesson 7. In the previous part of this lesson, we saw how to obtain a numerical solution for a time-dependent two-dimensional heat conduction problem. We validated our answer using data extracted from a Heisler chart, so this lesson we're going to take a quick look at Heisler charts and learn how to use them. So without any further ado, let's remind ourselves what these charts look like. Now, Heisler charts have been around for a very long time. We saw an application of one in the last part of this lesson. We used it to validate a numerical solution. But for a very long time, Heisler charts were the solution, because what they are analytical solutions, or non-dimensionalized analytical solutions, of an equation similar to partial d temperature by partial d time equals alpha, thermal diffusivity, K over rho Cp, grad squared T. And of course, we know that when that's written in vector form, we can drop it into any of the common coordinate systems that describe our problem. So you'll find Heisler charts for Cartesian coordinates, for cylindrical polar coordinates, and for spherical polar coordinates, depending on the geometry that that equation has been solved within. So Heisler charts are also specific to boundary conditions. Typically, what they are plotting are either temperature profiles through a geometry or temperature profiles as a function of time for a step change in temperature boundary conditions. And we're assuming that the temperature on all the boundaries is the same to start with, and it changes exactly at time equals 0 to its new value. So it's a very specific case of that equation's solution. And that is why, in a sense, we chose that very specific case in the previous part of this lesson. We're suddenly cooling the mold temperature to this, so we could make that comparison with a solution to a Heisler chart, so we could validate the solution. So Heisler charts were first published in 1947 in the Journal of the American Society of Mechanical Engineers, and they're still useful today for a number of purposes. As you've seen, we can use them to check calculations. They're a valuable source of data to do that. Or we can use them as they were originally intended, which was to quickly make estimates and get a feel for a problem. This second part has been largely forgotten about with the advent of quick and powerful compute. But for a back-of-the-envelope calculation or a back-of-the-envelope estimation, these charts are still very valuable. So, let me introduce to you the two major types of Heisler charts you're likely to see. And the first there on the board is a type that we used in the previous part of this lesson. What we're doing is we are plotting a temperature profile through a geometry. This is for a Cartesian geometry. So on the y-axis, what we have is the non-dimensional temperature. And that is expressed as the temperature at the particular point we're interested in now, which is T, minus T0, the initial temperature, all divided by T1, the new boundary temperature, minus T0, the initial temperature. That is plotted as a function of non-dimensional position, x over b. Now for this slab geometry, b is a half thickness, and a 0 value on that axis corresponds to the center line of the geometry. The various lines on this chart are all different non-dimensional times. And we can see that the non-dimensional time has been made non-dimensional with respect to the thermal diffusivity alpha, which is K over rho Cp. So these are very useful charts for getting an idea of the temperature profile in a material, be it a semi-infinite or infinitely long rectangular slab, or a sphere, or a cylinder. And the cylindrical and slab geometries we can directly relate to certain extra dates. The other type of Heisler chart you're likely to see gives information that we can use to judge convection and convective cooling. And so what we're plotting in these charts are again non-dimensional temperature, and note that it's been formulated a little bit differently to the chart on the left. And we're plotting non-dimensional temperature at a given position. See in the bottom left of that chart, and I've highlighted it in light blue, this is for r over r equals 0. So this is for a cylindrical geometry, and it's for the center line of that cylinder. So these charts are not a function of spatial position, they're for a stated spatial position. But what we're now plotting is that non-dimensional temperature, again as a function of time, for different BO numbers. And so Actually, we're plotting inverse BO number rather than BO number itself. So we can see that the lower the value of the inverse BO number, as in the higher the BO number, the higher the convective heat transfer, the faster the material cools. So we can use both of these types of chart either to validate numerics or to gain quick insight into a problem where we don't want to have to write numerical code. All right, so let's do some examples. One example of using one chart, one example of using the other. So let's look at the temperature profile in a semi-infinite slab. So the first thing I've done is draw my little drawing there. My semi-infinite slab is infinite in the length direction, but of a prescribed thickness 2b. Remember that b here is the half thickness of this geometry. X equals 0 here at the center of the slab. And so if we look at the chart, that x equals 0 line is bang on the middle. So if we want to work out the center line temperature, that's where we look. All right, so what I'm going to do is say, let's say my initial condition at time equals 0, my temperature equals T0 everywhere in the geometry. Then what I'm going to change when time progresses past time equals 0 is the boundary condition on the upper and lower surface of this semi-infinite slab. And so suddenly I'm going from T0 to T1, a step change. And if you recall, that's what we did in the last part of this lesson when we were looking at the numerical solution for that simplified injection molding problem. Okay, so that is the initial condition and the boundary conditions of the problem. And what I want to do is to use the Heisler chart to figure out how the center of the slab is cooling and how long it takes to cool. And maybe what I'm interested in is, let's say, that initial temperature difference between the hot temperature and the cold temperature. Let's say I get 90% of the way through that cooling. How long is that going to take me? Well, if I look at my Heisler chart, on the y-axis, 90% of T minus T0 over T1 minus T0 is where I've drawn that whacking great pink arrow. It's for a non-dimensional time of about 1. Okay, so what does that actually mean for us in dimensional terms? So let's convert that non-dimensional time into a dimensional time, and let's say that we've got 100 millimeters thick polypropylene, the same as what we looked at in our numerical solution in the last part of this lesson. That means to reach 90% cooling, it's going to take about 7.8 hours. And that is in line with our understanding that we gained in the previous part of this lesson, but we've achieved that understanding very, very quickly. We haven't had to write a mathematical script. We can just look at a Heisler chart, do a quick couple of sums, and we've got a feel for how long cooling is going to take. And so at that point we might decide, well, that's a silly thickness to have. We're not going to have that. We're going to do this a different way. And you haven't had to do the numerical solution in the first point. So it's a very quick way to get a feel for a problem. And remember, what I've said all along throughout this part of this course is that you've got to know the problem that you're answering and the precision to which you want that answer. What question are you asking here? Am I just interested in a feel for how long things take to cool? Well, if I am, use a Heisler chart. It's quick, it's easy. If I'm interested in the absolute details for a specific geometry, for very specific boundary conditions, then okay, maybe progress to your numerical solution, but don't forget to validate it, and a Heisler chart is a very useful way of validating it. All right, let's look at that second Heisler chart. It incorporates sort of a convection idea of thermal resistance. So that corresponded to a cylinder, a semi-infinite cylinder. It's semi-infinite in length of a prescribed radius. And again, let's look at how this is set up. I've got an initial condition at time equals 0, and that initial condition is that everywhere within my cylinder, my temperature equals T0. Then, as soon as time steps a little bit beyond 0, I immediately step change my boundary temperature to be T1. All right. Okay, let's look at this in terms of a melt spinning problem. So let's say that I've got a 4 millimeter diameter strand of polypropylene. It's quite a large diameter. Let's say it's in air. Okay, air's taking a certain temperature, and let's say it's more or less kind of natural convection-ish. Maybe my heat transfer coefficient H is 15 watt per square meter Kelvin. The geometry and material of my product gives me an inverse BO number of about 6. Okay, Fine. So the inverse BO number of about 6 corresponds to the line I've highlighted in pink on this chart. And we can see just by looking at that, this tells us that inverse non-dimensional temperature is changing rather slowly as a function of non-dimensional time. Okay. Let's say in my melt spinning line, I've got about 45 seconds to cool my strand down. So if I've got 45 seconds to cool my strand down, that gives me a non-dimensional time T star, alpha T over R squared, remembering alpha is K over OCP, of about 1. Okay, the lines I've drawn on the Heisler chart go from non-dimensional time of 1 up to my inverse BO number of about 0.6 and across to the temperature axis, and I've gone from 1 to about 0.8. So my temperature's fallen about 20% of T0 minus T1 in 45 seconds. So if I'm looking to get to 90% of cooling, 45 seconds is nowhere near enough, given an heat transfer coefficient of 15 watt per square meter Kelvin. A back of the envelope calculation reveals in order to get 90% cooling done in 45 seconds, I need a heat transfer coefficient of order 170 watt per square meter Kelvin. So knowing that, I can then see whether that's a feasible thing to achieve or not. And that was done all very, very quickly, wasn't it? No computing needed. The old methods for certain problems are sometimes still the quickest methods to do things by, because they were designed to be easy to be used by engineers to give good, practical engineering answers at speed. So, let's have a look at a few key points. Heisler charts are basically graphical solutions using separation of variables to the energy transport equation in a time-dependent formulation. You can get them for slab geometries, cylindrical geometries, and spherical geometries, and they are subject to very specific boundary conditions. That is in effect their weakness. You're basically saying all my boundaries are subject to the same temperature, and that is a step change in temperature from whatever initial temperature it was to whatever temperature it is now. But sometimes we can use that to get a very good feel for a problem. They're also a valuable source of validation data for numerical calculations.